So after 2 days of talks on parallel computing, I thought I would try something a little different and talk to you about systems of public transportation. So what we have here is TRAM. How many people don't know what a TRAM is? Okay, that's what I thought. However, I read on the internet that some Americans don't know what a TRAM is. So there it is. I'm not sure how clearly you can see this photo, but essentially it's an electric train. And this is the whole idea of why we're talking about TRAM. Because what we have here is a situation of a traffic deadlock. Just imagine if you're in one of those cars on the right, you're sitting in traffic, not moving at all. Meanwhile, the fellows in the tram on the left are moving right ahead. They get to their destination on time, and they can have a nice day. So this is somewhat in jest, but really what TRAM is in this context is Topological Routing and Aggregation Module. So let's just go quickly through each of these words just to make sure we're on the same page. By topological, it means that we'll be working with exploiting physical network topology. Routing, of course, deals with determining the message path when sending messages over the network. Aggregation is the combining of messages, particularly fine-grained messages, into larger messages. And module just means it's a component of a larger system. In this case, the system is Charm++. So Celso mentioned mesh streamer. And yes, at this point, mesh streamer and TRAM are essentially the same thing. Mesh streamer, the way I look at it, it's the name of the prototype implementation for TRAM. We'll go into the details later, but the main constraint for mesh streamer is that it only supports virtual mesh topologies, versus TRAM will eventually be more generalized. So mesh streamer was developed for the 2011 Charm++ HPC challenge submission. That was around the time that we were implementing all of the benchmarks that are required, and we found that for the random access benchmark, we needed a library that would perform message aggregation to improve performance. And we had success with using this approach. It wasn't a brand new approach. There was research done at IBM before that, and even before that by one of Professor Kale's students who, by one of Professor Kale's previous students who went on to work at IBM. So the first question is, why are we looking at aggregation of messages? Well, it turns out that sending a message over the network involves lots of overhead. So you have to allocate a buffer for the message. You have to serialize your data that you want to transfer over the network into the buffer. Then you have to inject the message onto the network. The message needs to be routed to the destination. Eventually, it will get received where the runtime system will pick it up. But then it will need to schedule the message. In the case of Charm++, it will need to schedule the entry method corresponding to the message. So that's quite a lot of overhead. And in fact, with TRAM, we don't target all of the overhead I just described. Some of the overhead is dependent on the size of the data. So, for example, when we talk about serialization, if you have a large number of data structures of significant size that need to be serialized into your buffer, this may this will be dependent, the time required for performing that operation will be dependent on the size of those data structures. Now, some other components of those of what I just described. So, in particular, scheduling is not really dependent on the size of the data, and so this is something where if you can combine multiple fine-grained units of communication into a larger message and send it at once, you may be able to avoid some of the constant sources of overhead that don't depend on data size. So we can talk about two sources of constant overhead. What I just described was mostly processing overhead, such as scheduling the message when it arrives at the destination. But there's also a bandwidth component to this. Because as it turns out, I don't think this will come as a surprise to most of you. When you want to send some bytes over the network, it turns out that you have to send more bytes over the network with what you're sending. Back when I first started in Professor Kale's group, I was confused about people talking about sending 0-byte messages. It just seemed very mysterious. I assumed that what they were in fact doing is sending, a very small message, perhaps 1 byte or 4 bytes, because really, how can you send something that has size 0? Well, it turns out that I was right, because in fact, what you're doing is sending at least 48 bytes in the case of Charm++. For MPI, it's less than that because the size of the message header is smaller. But the overall idea is that whenever you send data over the network, you'll have to attach a header to it. So you'll have to, the runtime system, when it picks up the message on the receiving end, will have to know what to do with it, and that's where the header comes in. In addition to the message header, there is additional bandwidth overhead that comes from the network. So in particular, when the network hardware performs the routing, it may attach a few bytes here and there for the routing. It will also do so to make sure that data arrives without any errors. And also, most likely, it will convert your large message into packets. And when you do that, when you do that, the final packet of the message will probably be partially filled, and that will correspond to data that gets sent but is not useful. So network bandwidth is somewhat tricky to deal with. What people usually try to do is consider it as a single value. So people will talk about bisection bandwidth. Here we do something similar where we actually just take the bandwidth across all of the links in the network and we just add it up. And the idea there is that if your application is communication bound, that is, it's limited by the bandwidth of the network, and it's relatively equally balanced across the system, then this approach makes sense. Essentially, any link's bandwidth that you consume will negatively impact your performance. So we talked about, I mentioned fine-grained communication, but why is it that we are only focused on fine-grained communication? What about large messages? Is it the case that they will not have the constant sources of overhead? Well, that's not true. They will. It's just that if you are sending large amounts of data, the constant overhead will not be of significant enough size that you will need to worry about it. You'll have larger problems due to the bandwidth of sending the large amounts of data, real data, not the message headers. And sometimes people think that in HPC you don't really have fine-grained communication as long as you write your application carefully. So maybe I've heard people saying that, well, you know, I've performed grain size adjustments in my program, so my messages should be of sufficiently large size. I shouldn't really have any large messages. And sometimes that is true to some extent, but then you also have things at the runtime system level like acknowledgments, requests, control messages, and such. And you also often have these things in application codes. And the other thing here is that for strong scaling, it may be the case that at lower node counts, your messages are large because the grain size of the work on each processor is large. But as you strong scale and you increase the number of processors, eventually you will be running into smaller and smaller messages, just because you're partitioning the data into finer and finer units. So then we should talk about routing. I mean, TRAM is topological routing and aggregation module. And this is, in some ways, maybe the more tricky aspect to explain. And I thought about kind of a good analogy for this, and a good way to explain why is it that we are looking at routing. But first, I should mention that by routing, I'm not just referring to picking the path for a message from the original source to the destination. That is part of it, but the more significant aspect is what you do at intermediate points in the path. That is, we will be selecting intermediate destination nodes for each fine-grained data unit that needs to be sent. And at these intermediate destinations, we will be recombining the particular data units in order to improve aggregation. And the best, I think the best analogy I found for this is actually going back to the public transportation bus. So how many people went on the Blue Waters tour yesterday? Okay. So how many times did the bus stop along the way?
Oh, I drove. I didn't.
Okay. How many people took the bus? Okay, so Tom, how many times? Okay, so the question then is, why does the bus stop along the way? I mean, why don't buses just go in between two destinations back and forth? I mean, it's a silly question in some ways, but it really, when you map this problem back to a communication framework on a parallel system, it's something that's actually done very often. I mean, we are sending tiny units of communication, and we're not really considering the opportunities of combining them into larger units. So, does anybody want to venture an answer for this pretty simple question?
In order to carry all the people where they wanted to go, you need a lot more buses.
Okay, that's a good answer. Also, what happens with every kind of intermediate destination at which you stop? Some people get off, other people get on. So essentially, you're serving a lot more possible routes by stopping at these intermediate points. And it's similar with the approach taken by this TRAM library. Okay, I think I already described that. And we'll go back to that a little later. But first, let's look at why we're talking about topological routing. So it is infeasible to have a separate hardware network link between every pair of nodes in your system. If it was feasible, then we wouldn't have to worry about anything. We could just send messages and always be certain that the bandwidth would be equivalent between any pair of nodes. But So as it turns out, when you send a message, that message will travel typically over a number of links along the route to the destination. And now this is typically invisible to the application and runtime system. So what we want to do is we want to lift this decision making into the realm of the runtime system and take advantage of the intermediate destinations. So this is a picture showing what happens when you have large units of data communicated over the same link at the same time. What you have is that you run into congestion. And with TRAM, of course, the messages will be larger than normal, so you really want to avoid it. So there are various network topologies that are in use currently. There's no single one that has kind of been accepted as superior, although on the right you have a picture of the Perks topology from one of Abinov's papers. And some people are saying this is the future of networks, but currently at least these three are all pretty common. You've got fat trees for InfiniBand networks. You've got the torus systems like the Blue Gene and the old Cray systems. Well, not old, but so we talked about topology. Now, with TRAM, in addition to the physical topology of the network, you also have a virtual topology component. The virtual topology is what TRAM will actually be working with. That is, you take the nodes in your program and you map them from the physical topology onto the virtual topology. And then within this virtual topology, TRAM will be employing the routing. And now you see why we're talking about topological routing. If the match between the virtual topology and the physical topology is poor, then when you perform routing with intermediate destinations, you may be moving across most of the system with each intermediate destination unless you map the virtual topology such that it corresponds to the physical topology. And when we perform routing, there is a little bit of a danger in that we will be making routing decisions in software, but we should be aware that every time we send a message, even if we are sending to an intermediate destination, there's a danger that the hardware will perform indirect routing and the message will not travel along the path that we expect. But on some systems like Blue Gene, it is like Blue Gene P and Blue Gene Q, it is relatively easy to guarantee that as long as you are traveling along a linear direction within a single dimension, you should not run into this problem. And the other thing that we want to guarantee with TRAM is minimal routing. It ties into what I just talked about. That is, even though we have intermediate destinations, we don't want our data to travel over more links than absolutely required to reach the destination. As it turns out, it's relatively easy to have a good mapping of virtual to physical topology in Charm++. For this aspect of TRAM, we use the Charm++ Topology Manager, which essentially gives us the physical topology information of the network. And because MeshStreamer works with a virtual mesh topology, it was relatively simple to then define the virtual topology that maps the physical network topology. So with TRAM, what we're working with is small units of communication. Basically, the user will define an instance of TRAM and define the type of data units that can be communicated with TRAM. And currently, that is limited to a single data type. And we call each instance of that data type that gets communicated a data item. So in the context of TRAM, only what are called peers communicate with each other. So it's no longer the case like when sending messages directly that each node needs to be aware of everyone else in the whole topology. Instead, you're only communicating with a very limited number of peers, and it's within this set that you pick the intermediate destinations for the data items when they are sent. So now here is the mesh routing algorithm that we use. Essentially, you order the n dimensions in your virtual topology, and within this order, you take a data item that gets submitted to be sent, and you consider the index of the destination for that data item. And then you look at your order of the dimensions, and you consider the first index in that, the first component of that index that does not match in the final destination and the current node from which you are sending. So it sounds a little complicated, but if you see what actually happens within the topology, here you have a three-dimensional mesh topology. What will happen is that if you have three data items that are submitted on these three processes here, those will travel along the first dimension that is the planes of the topology. That will travel to the destination's plane. The destination, by the way, is that red square here. And eventually, along the route, all of these messages will get combined into a single one, and they will be delivered as a single message at the destination. So when we talk about aggregation of data items at the source and each intermediate destination, there's the question of how aggressively should we aggregate. Do we use a timeout? Do we aggregate based on the size of the buffer? And it turns out that aggregating on size of the buffer works pretty well. That is, if you allocate all of your aggregation buffers to be of size 4 kilobytes or slightly larger, 8 kilobytes or 16 kilobytes are two other choices. At least on this system, which is BlueGene-P, you reach a very high fraction of the total link bandwidth. With smaller messages, so for example, here you have one kilobyte messages, you only reach about 40% of the available bandwidth for the network. And this is good news for the memory footprint of the library, because if we can afford to only aggregate 4 kilobytes per peer, and the number of peers is limited, then it turns out that the memory footprint of TRAM will be limited as well. And we heard Keith mention this because TRAM is being used for episyndemics, and there they found that they could just use a manual aggregation approach where they aggregate messages separately for each destination in the whole system, but that would lead to a somewhat heavy use of memory for the buffer space. In comparison, when using TRAM, the memory footprint is much lower and the performance is comparable. So the usage pattern for TRAM is that you initialize the library and then perform sending and receiving of data items. But you also have to have a termination step to indicate to the library when it can perform flushing of all of the buffers globally. Now the library will be flushing all along as the buffers fill up, but chances are at the end you will end up with partially filled buffers. So the termination step is required to get those sent at the end. So what is this library good for? So we've done some tests with benchmarks and applications. This is sort of the most basic benchmark that you can run with this, which is an all-to-all benchmark. And what we have here is BlueGeneP results for all-to-all with various amounts of data sent in small units. So even if the data sent from each process to each destination is, say, 4 kilobytes, in all of these runs, the data is sent in units of 32 bytes. And that's to take advantage of the aggregation approach with small data units. So what we have here is 2 runs at 16K and 32K nodes of BlueGeneP. The green lines are at 16K and the red ones are at 32K. And as it turns out, we get about a 3 to 6 times speed up for the various cases when using TRAM. So that's very substantial. The other place where we tried TRAM is with Changa. So that's the cosmology code that Tom just talked about. And here we used TRAM with the small data unit, small messages that Changa sends to request data from other processes. And it turns out that those are so numerous that combining them leads to a relatively noticeable performance improvement here. We see that it's about 15% throughout most of the area in which the application scales. And as we work on improving the scaling of the application, I hope that we can notice an even larger improvement toward the right. And I mentioned epistemics already. So there the idea is to combine the messages that go from each person to a location manager. And so the researchers at Virginia Tech have tried a manual aggregation approach, and that's actually what they end up using at higher node counts, because it turns out that eventually there is some bottleneck in TRAM that prevents scaling at very high node counts. But at least in this realm, between 128 nodes and 2K nodes, and this is on blue waters, at least in that realm, there is actually some speed up from TRAM. And I think with time, TRAM should be able to outperform the manual aggregation approach. So here I'll briefly talk about what the future, what are my future plans for developing this approach further. So currently, TRAM is a library, which means that users have to be aware of it and have to tune it and implement its usage into their applications. And it turns out that that's a little more involved than you would like it to be. It does take some coding effort. And so our approach will be to develop an autonomous system such that users don't really have to be aware of the tuning parameters and such. And they can just get the benefits of aggregation without being aware of a system running behind the scenes and combining messages for that. And also, currently with the mesh streamer prototype, we are only using virtual mesh topologies, and as it turns out, it may be beneficial to use other types of topologies. So we will be investigating that. Okay, thank you.